Hi, let's take a look at one more enzyme for class 7. It's also a general base and general acid enzyme, carboxypeptidase A, just like HIV protease, but also it's a metalloenzyme. And I like this picture a lot. It's a structure where you see the zinc right in the middle, the silver ball, and it's surrounding by, see those red residues? That five-membered ring, that's histidine. So there are two histidines and one glutamic acid. And that zinc is very important for the general base and general acid mechanism for this particular enzyme. Okay, here's another representation of the carboxypeptidase A, and you can see the zinc right in the middle. If you look at the certain residues that are binding that zinc, you have glutamic acid, histidine, and histidine. And what's happening here? You know that histidine has that nitrogen. So that nitrogen lone pair, how am I going to draw this? Is making a non-covalent interaction with zinc. Actually, it's you could think of this as a dipole ion dipole interaction. Glutamic acid in this state is deprotonated, so you have definitely your O, and there's resonance, right? And you have a partial negative for glutamic acid. Let me jot down a couple more facts about carboxypeptidase A. You already know that it cleaves at the C-terminus when we were looking at peptide sequencing. Carboxypeptidase A is a digestive enzyme produced in the pancreas. It is very important with other processes like digestion, post-translational modification of proteins, blood clotting, reproduction. It cleaves or hydrolyzes at the last amino acid at the C-terminus, and it cleaves faster if that amino acid has a bulky nonpolar R group. It's a single chain with 307 amino acids, and 38% of it is in alpha helix, 17% in beta sheets. Here I have the pKa's. So what is this? This is the pKa of the metal-bound water. You see that here for the zinc. Okay, so that proton is pretty acidic. In terms of basicity, we can rank where this metal-bound water is. So let me go back to this table. We know that water itself has a pKa around 15.5. So when that water molecule is bound to a metal, we're going to look at zinc. It drops to 8.7. So this talks about the acidity. The acidity of metal-bound water. Now, when that water loses its proton, then you have the conjugate base. So here is the list of basicity. You have the hydroxide as a very strong base, followed by the metal-bound water that already lost its proton, followed by water. Carboxypeptidase A is, just like HIV protease, a general base and general acid catalyst. Let me remind you an easy way to remember what general base and general acid actually mean. These are ways to describe general base and general acid. For general base, the proton is removed from the reactant during the RDS. Remember that if you take a look at our notes from a previous video, a specific base is where you have the full deprotonation of one of the reactants, right? And that now that O- is attacking, eventually to cleave a bond, in this case an ester. That's specific base. But in general base, you see how we never get an O- because the proton is removed at the same time that the reactant attacks this carbon of the carbonyl. So it's at the rate determining step. It's shorter, typically. The general catalysis is shorter than the specific catalysis. Okay, so we're going to see something like this in carboxypeptidase A. This was from a previous video. For the general acid, which is the second step, the proton is transferred to the reactant during the RDS. Well, here we never see a fully positively charged reactant like we do in a specific acid catalysis, and we get this intermediate. Full transfer of the proton before the RDS. What we're going to see is that we're going to transfer the proton at the same time that we're going to attack this carbonyl. So at this, again, the general acid catalysis is shorter, right? One step, versus specific acid where you create this protonated intermediate before you do the RDS. Let me show you the mechanism for carboxypeptidase A. It's going to be two steps only. One, the general base catalysis, followed by the general acid catalysis, and by then we'll have the peptide cleaved. Also, we can't forget, unlike HIV protease, that metal is going to play a role. Alright, so look how I set up the peptide that's going to be cleaved at the C-terminus. It looks like in the enzyme we have a protonated arginine that's stabilizing or interacting and holding this peptide in place at the C-terminus. We got our zinc, and that zinc is held into place as we saw before with three residues, histidine, histidine, and glutamic acid, deprotonated. So that those three amino acids are here holding the zinc, and here's the zinc-bound water. Now, if this was a specific base catalysis, we would have OH minus made first attack this carbon of the carbonyl. But instead, this is general base catalysis, and what we're going to do is, this is fairly acidic, right, when it's bound to the zinc. We're going to grab this hydrogen, and then now we're going to attack. Very similar to HIV protease, except HIV protease didn't have this metal holding the water there. Okay. And then what happens is, when you attack the carbonyl, you go ahead and make the anion, the oxygen anion. Okay, those are the three arrows for the general base catalysis. Let me double check actually if it matches. Yeah, here's same thing. Three arrows for the general base catalysis to make the oxygen anion. Can you draw the result based on my arrows? And also, do you know how these other parts of the system look like after these three arrows? The result of these three mechanism arrows is now we have the tetrahedral intermediate. And just like we saw in HIV protease, we have a stabilization of what's going to be the transition state. We're using the zinc metal atom to do the stabilization of the oxygen anion. I'll let you look up, or if you can recall, what was the thing stabilizing the transition state with HIV protease? Do you recall that? Okay, next, what happens here? We got to do a general acid catalysis now to break which bond? Remember, it's this one right here. So how do we do that? We are going to take, well, first thing is you're going to reform the double bond, reform the carbonyl, start there, and now something has to break. This is going to break, grab that hydrogen, and then we're going to reform the oxygen anion that was originally there. So we're getting back our catalyst. Our catalyst will look exactly like this when we are through. Okay, go ahead and draw the result. As you can see, the result is we made that cleavage. We have our C-terminus amino acid right here. That's released. And now zinc is ready to have another water be bound to it. So eventually water will come around and you'll form this non-covalent bond. Before I wrap up this video, there are a couple things I want to say about metalloenzymes. About 1/3 of all enzymes involve a metal. You saw how useful it is to lower the pK by using that metal. Lower the pK of water, so you can participate in a general base catalysis. But there are other options for that metal to help polarize a bond. For instance, if you have a carbonyl group of a peptide, maybe, like this. Well, if you have a bond to a metal, right? Well, this oxygen is building up a partial positive charge. Let me get my colors correct. Okay. Which makes this carbon very attractive to a nucleophile. Okay. So instead of the metal binding water to make it more acidic, you could bind the oxygen carbonyl to make it more nucleophilic. Another option would be something like this. If you want to break a carbon-oxygen bond, for instance, instead of protonating that oxygen, you could have it associate with a metal, and that will also polarize the bond and make it weaker. And you have this set of arrows. It facilitates this bond breaking.